Okay. So last time we left off on this material here, I believe. Yes. We left off on here last time. These were the intermolecular forces and how they related to various different physical properties. Remember, is that okay? Okay, if you have more intermolecular forces, then typically what are you going to have a higher up? Boiling and melting points, right? You're going to have higher boiling and melting points. Okay? Okay. And what else causes you to typically have higher boiling and melting points, by the way? Yeah, the mass. So a higher molecular weight is typically going to mean a higher boiling and melting points. Very good. Fantastic. Now, one of the things we haven't talked a lot about is surface area. So remember that when we're talking about induced dipole, surface area is a huge part of that. Okay? If you want to have more friction, what do you do with your surface area? Like my mass is the same either way right now, right? If I drag my hands along the table with just my fingertips, I don't have a huge amount of friction, right? If I do it with my palms, I increase my surface area, I have a lot of friction, right? And so, again, we're seeing this same sort of trend, aren't we? And when we're talking about induced dipole. So if you have something like normal pentane, you can actually put small n dash pentane to denote, hey, this is the just straight chain form, normal pentane. These will overlap very nicely, kind of like Pringles in a Pringles container, right? And so they overlap very nicely on top of each other, they stack, and what you see is the boiling point ends up being 36 degrees Celsius, because you can do induced dipole among each of these pairings. See that? So that's very nicely stacked. Now, if you have a highly branched instead, what you see is the boiling point actually goes down to 10 degrees Celsius. And that's because when they try to stack, they have very little surface area in contact, right? So any induced dipoles that are happening inside of here don't mean anything. They don't help. Okay? It's only the ones at the surface here that matter, that are going to actually cause you to have a higher melting or boiling. Okay? All right, now solubility. The general rule typically is like dissolves like. Remember that this is a general rule. This is not everything there is about solubility. I'm done now. Okay. Like many of the things I talk about, general rules can be broken in a multitude of different places. They're general rules because we have generalized to make it easier. Okay. So polar compounds tend to dissolve polar compounds. Nonpolar tend to dissolve nonpolar. Nonpolar compounds like hexane are going to be insoluble in polar solvents such as water. This is actually what you're seeing when you have like gas and water on a like a gas station. See the puddles at the ground, right? And then on the surface, you see the gasoline, and it makes that shiny surface. That's what you're seeing. Gas, hexane is a part of gas. It's one of the components. And so it's not dissolving in water, right? The solubility is going to be the result of those intermolecular interactions. Anybody ever have like magnets when they were a kid? Okay. I've been told that they don't really do this anymore, but they used to have, when you bought Lego sets, they would have magnetic pieces in them. And you could do like little magnetic things where you can like have the guys walk along magnetic surfaces and attach them there instead of clamping them down. Do they still do that? No. Yeah. Yeah. So does anybody have any case where you had magnetic things with non-magnetic things in the same bag? Yeah. Can you think of that idea? Okay. Can everybody conceptually envision that? Right. So if you threw magnetic pieces, little magnets, in with non-magnetic pieces, okay, what would happen inside that bag? You know, I'm carrying around with me, jiggle, jiggle, jiggle. Okay, they get mixed. What happens? All the magnetic pieces clamp together, right? What's going to happen to the non-magnetic pieces? Yeah, they're going to get pushed off to the side, and they're going to get excluded, right? So that's actually what's happening when you have water and gasoline. The waters are all snapping together, right? And they're going to make a nice water structure. Are you going to have maybe a few gasolines get caught in the middle? Yeah, sure. Okay. But the vast majority of those gasoline molecules are going to get pushed off to the side, right? And they'll form on their own. Okay. And that's actually what you see when you see like versus like. The stronger intermolecular attractions snap together, and the weaker ones get excluded. Okay. There you go. Now, the solubility is going to be a result of the intermolecular interactions again. An increase in entropy is actually what provides that driving force for the two substances to mix. Does everybody remember what entropy is? Can anybody give me the definition you were given? Mm-hmm. Yeah, that's not a bad definition. It works for most cases. So it's increasing disorder, right? Is probably the definition. Yeah. So if you want a more complete definition, you can actually do what's called microstates. So microstates are what's called the individual states that things could be in. Okay. So with this number of students, we have one microstate, which is this state right here. You each are in your desk like you are. Okay. And then we could have you guys swap, right? And you two could be here. That'd be a different microstate. And then we could swap you two. That'd be a different microstate. Okay. The more microstates you have, the more disorder you have, the more randomness, right? And that's what entropy is. And that's why entropy actually is what drives induced dipoles as well, is because you have different states those electrons can be in. And they will, as you go through probability, everybody knows that, yeah, 50-50, you flip a coin, it lands one on each side, right? But if you sit there and flip coins, does it go heads, tails, heads, tail, heads, tail, heads, tail? No, no. And in fact, I'm like weird. I have really, really bad luck. And so if you ever want a statistic thing and you want me to do like hey, I'm going to include you in this study and we're trying to get this statistical result, do not include me. I will wreck your study. Absolutely wreck it. Okay? Somebody tried to do, the curtain thing where you have 3 curtains, you pick one. Then Bob Barker says, this one, curtain 2, is not the thing. We eliminate it. And then you're supposed to change and it improves your probability of getting the right answer. Okay? I did a 99 losses out of 100. So I did that and lost 99% of the time. It's supposed to bring a 33% of the time of winning to approximately a 66% of the time winning. I won 1% of the time. Oh, do not have me do probability. But that has to happen, right? Like if you have, somebody has to have a string of runs. I also have done this, by the way. I've had 30 tails straight when I was trying to get hit. I've also rolled a natural 1 on a D20. Anybody play D&D or anything? I've done that 27 times in a row. Don't depend on me for stats, okay? I am like a confluence of all the like outlier events that should happen in probability. So when you're talking about probability, like that outlier event, if you have enough people doing it, somebody will get that outlier. Okay? Somebody will get, if you did trillions of coin flips, somebody's gonna flip heads 100 times. Okay? And the same sort of thing happens in all probability. And when you talk about entropy, the same sort of thing has to have happened. Okay? And that's how probability actually works. People don't think about that, but individual events do not have to be probabilistic, right? Yeah. Okay. They just have to fit in the overall probability of all the events. Now, again, did everybody understand the microstates when I talked about them? So it's the individual possible states of a system. The more microstates, the more individual states you have, the greater the entropy or randomness. Okay. Okay. Now, when we talk about when we're talking about dissolving things, now can everybody understand how entropy actually is increased by dissolving things? Okay, so like when you start dissolving everything, everything's trapped in one spot, right? When you dissolve things, they're going to be split up and you have more possible states they can be in. And so the randomness increases, the entropy increases. Okay. Okay, now substances tend not to mix if the intermolecular interactions in your pure solute and pure solvent are going to be sufficiently stronger than those in the hypothetical solution. So think of it like this again. If you put an object between two magnets and it's slick, like a marble, right? Then the two magnets are going to try to pull each other past the marble and it's going to slip out of the way. Okay? And so to get something to dissolve, their intermolecular interactions have to be pretty close. Has anybody ever seen the experiment where you take isopropyl alcohol and water and you put salt in it? Or ever heard of salting out vodka? No? Moonshine? No? That's sad. Disappointing, even. What are you people doing with your lives in Tennessee? But if you don't know anything about moonshine and well, I guess vodka is not the right one, but whiskey, um, then that question has to be asked, right? I guess we're in the wrong county technically. I think that's it. So if you put salt into alcohol water mixtures, normally the alcohol and water have pretty similar intermolecular interactions, and so they're what's called miscible. They can dissolve each other in any quantity. That's why you can have 90% alcohol, 50% alcohol, 10% alcohol. Okay? Because miscible, any quantities. If you put salt into that, enough salt, what you'll actually start seeing is the alcohol and water will start separating. And that's because the salt dissolves better in the water, and then the water's held better together by that salt-water bonds. Okay? So you form the ion dipole interactions. The ethanol doesn't do that as well, and it gets excluded. Whoa, huh? Do you know you can ice out alcohol as well? That's why you can't freeze alcohol. If you freeze alcohol, you can go to jail. Do you know who raids you if you freeze alcohol? It's the DEA. They have tanks, helicopters. All their agents are SWAT team members. You can actually do it for yourself. So as long as you do it for yourself, you can brew alcohol, you can distill alcohol, all that. Okay. If you sell any amount of it, the federal government goes after you because it's one of the primary sources of revenue for the federal government. Is the sale of distilled alcohol? They tax you on. So you can freeze alcohol if you go cold enough. Most freezers will not go cold enough. You need a negative 80 freezer typically. So if you use the one over here, I think we have a small negative 80 freezer. You could freeze alcohol. It'll freeze the water actually, and it will actually concentrate the alcohol. So if you're very careful warming it back up, you can extract much purer alcohol. You guys are like, oh yeah, we're trying this now. Sounds like a party. So it does become more difficult to freeze water when you add alcohol to it. That's why your normal freezers don't do it. And that's literally because you have to break up that entropy. You're undoing the entropy when you're doing that. Yeah. So it becomes much more difficult. Okay. So this right here is water and hexane. And so you throw together water and hexane. Now, to emphasize this, we're talking about naturally they will separate and make two layers. Okay? They won't stay mixed. But if you sit there mixing them the entire time, you can force them to be mixed temporarily. Okay? You just have to continuously put in energy. And that's because it's hydrogen bonding versus induced dipole only. Now, does water have induced dipole? Yes. Yeah. All molecules, all atoms have induced dipole. You just don't care because hydrogen bonding is so much stronger, right? So, yeah. Now, another way of looking at that, by the way, is that did you guys know that fatty acids have induced dipole interactions? Yeah, right? Because that's what you typically think of as fats dissolving stuff. Did you know they also have hydrogen bonding? No, you don't think about it because it's so much less than that amount of induced dipole. So, now this is pure ethanol mixing with water, and what you see is that the pure ethanol can slot in pretty successfully. So successfully is that if you have methanol or ethanol, it can just be miscible. Propanol also would be miscible, in case you're wondering. Butanol is going to be on the edge of that, so you can start separating those if you're not careful. Okay. So the strength of an ion dipole interaction is going to be intermediate. That's between that of an ion-ion interaction and that of the dipole-dipole interaction. So if you were to take an ion dipole interaction like this right here, this is kind of like what you would see for like a soap or something. This one right here would be, again, the other ion dipole interaction, right? And so it's going to be the intermediate between the interaction between these and these. So if you took the interactions for those two, averaged them out, you'd get very close to this interactions here. Okay? Okay, so this right here is how you actually do solvation. And so when an ion dissociates into a polar solvent, many of the ion dipole interactions are going to result. You'll have little clusters of dipoles around the ion that enclose it. Okay? And this is actually what we refer to as solvation. So when you've been dissolving ions into water, what you're really forming are little shells of water around the ions. Those shells then interact with the rest of the water. Okay? And yes, they do have a set organization. They're actually pretty highly ordered. There's a little bit of chaos and randomness to it, but not as much as you probably think. Okay? And yeah, they kind of look like this, but three-dimensional. Yeah. Anybody have any questions about that so far? Now, when you do this process, do know you literally have a crystal. It has those ions in it, and you have these little dipoles coming around one side of it. They start pulling that ion out, and then you have another one wedges itself in there, starts pulling it out, and then so on. Okay? And then eventually it detaches, starts floating around on its own in the water with its little shell. Okay? Okay. So do note that we have increased entropy when we do this, haven't we? We have more positions we can be in. Okay? It's one of the primary driving forces to this. Also note that what happens if I don't have enough energy to allow these things to actually break those connections? Will I ever dissolve? No. No, you can actually put it with not enough energy to dissolve. That's also why when you hit it, i.e. stir, you can cause it to dissolve faster. You're literally hitting this and breaking the bonds with your hitting it. Yeah. Okay, so in which solvent would you expect NaCl to be more soluble? Diethyl ether, which is right here, or propanol, which is right there. Which one is more soluble? Don't give your answers away to people. You can talk about them to the person like next to you and stuff and try to reason through, but try not to like wholesale give answers away to the whole class, because what will happen is people will fixate on one person's and they won't think about it. Okay? They'll just. It's why the wisdom of the crowd only works if you guys don't talk to each other. I'm going to move on pretty quickly on this one. I want you to think first, though. Okay, so what we're having to do here is we have to break these very strong ion-ion interactions, right? And so when we dissolve NaCl, we're breaking up those ion-ion interactions. So the dimethyl ether and propanol, these are both polar molecules. They both have oxygen-carbon bonds. They're both going to make ion-dipole interactions. So those are actually quite similar, okay? So what we need to look at is what's going to have the greater dipole? What's the bigger magnet to do this with, okay? And so if you look at the propanol, it's going to have a carbon, oxygen, like so, okay? And then the other one's going to have the oxygen between the carbons, right? Everybody okay with that so far? So this one, if we look at the bond dipoles, is like this. And then that is the molecular dipole, right? This one, the bond dipole is like this, and molecular dipole is the same thing as okay. So this one here, we're actually canceling off part of that, aren't we? Can everybody see that? These ones on opposite sides, that vector's canceling. Okay? So we only get part of this oxygen pulling carbon. And so we get a much weaker bond dipole than here. A little bit, but realistically, it's more like having when you see these double bonds, it's actually more like thinking of it as two separate ones that are all lined up. It doesn't quite add up to two separate ones lined up, but close enough. Good enough. If that makes sense. Yeah. So effectively it's like having two of it. And so it's like this case, but we line them both up, right? Good question. All right. Anybody have any questions about that? Everybody understand the reasoning there? Yeah. Yep. Okay, fantastic. Let's talk about some of the effects of these hydrocarbon groups on solubility. So functional groups will influence solubility of a compound, of course. Small alcohols are going to be soluble in water, and it's because they can form hydrogen bonds with the water. It's called hydrophilic, water-loving, right? They're going to form hydrogen bonds with the water, or they're forming dipole-dipole interactions with the water, and they're going to be able to dissolve in the water. So they love water. They like to dissolve. If they have large R groups, they're highly nonpolar, then it's not going to be like versus like. And so this is going to be called hydrophobic, meaning water fearing, right? So they're going to exclude from the water. They're not going to dissolve in the water. Okay. So the water solubility of an alcohol is going to decrease as the size of the group off of the alcohol increases. You can think of it as having more hydrogen bond character versus non-polar character, right? Or more polar versus non-polar character. Okay. Now, what happens if we add more hydrogen bonding groups on? We increase the polar character, right? And so that's actually what you're seeing right here. That's sucrose. This is why sucrose is water soluble. You know sucrose, right? One of the common disaccharides you can buy in food. Okay. Less common than fructose, but okay, so right here we have sucrose, and see all the OHs off of this? Those can each make hydrogen bonding to water, and so this is pretty soluble. Is it miscible? No, you can put too much sucrose. Okay, versus something like methanol or ethanol, where it's miscible. It's infinitely soluble. Okay. Okay. Now, molecules are generally going to be very water soluble if the ratio of the total number of carbon atoms to the number of hydrophilic functional groups is less than about 3 to 1. And so that's why, for example, we were talking about methanol, ethanol, and propanol, and these are miscible. Butanol is very water soluble. Don't get me wrong. That is pretty water soluble. 7.7 grams per 100 grams is pretty soluble. Okay, but it is not miscible by any means. Okay. Miscible would mean that it can be 100 out of 100. So 100 to 100, that you can have equal amounts. Okay? Mm-hmm. It's the ratio. Yeah, so every carbon is nonpolar. And so as we go out here, this amount that this pulls this in is slowly getting eroded by each carbon. Okay? And we're more and more losing ground. And the waters are squeezing us out a little more each time. When we get to this point, we're past the 3-to-1 ratio. So the 4-to-1 ratio starts getting pushed down. And you can see it drops off pretty quick, actually. So we, a third, and then a third again, and then we're almost insoluble, really. At this point, we're basically insoluble. We can dissolve a little in, but almost nothing. Does that make sense? Anybody have any questions? Okay. Again, this is just a sort of generalized rule. You want about 3 carbons for every 1 water soluble thing. This could be an amine. This could be carboxylic acid. This could be OH, alcohol. Note that this ratio is not perfect. Okay, like if you have an amine or if you have a double bond, a carbonyl on this could fall off a bit more on this one. Okay, and this could maybe not be infinitely soluble. Okay. Okay. So, would you expect each of the following compounds to be soluble in water? Why or why not? So, we're looking at that ratio again, right? So, we want it to be 3-to-1, means it's what? Soluble. If it's not 3-to-1, if it's more than that, not soluble, right? In the case of the alcohol, you could consider that soluble to some degree, but typically your insolubility for most of these compounds will fall. Like this is going to be past. It's definitely insoluble if you're past that. Like we're already at the point of just one of those, getting to the point where it's arguable whether we consider that soluble. Okay. You can only put 7 grams at 100. You can't even get to 10% solution. Okay, folks. So also consider why and why not. Why would that be? Okay, because the trend's actually the more important thing to take from these. All right, so this right here, again, we're looking for a 3-to-1 cutoff, right? So this right here has 1, 2 OH groups that are water soluble, right? And then we go to here and we have 1, 2, 3, 4, 5, 6. And so we would expect this to be highly soluble, okay? Because again, that's 6 divided by 2, that's 3-to-1, isn't it? This one right here, well, that's 6 versus 1, isn't it? That's a lot worse than that. That's very insoluble, okay? This one right here, yeah, even worse, right? Yeah. That's definitely not. By the way, naphthene is this sort of structure is what you commonly see in things like mothballs, in case you're curious. Okay. That's where you would have like seen stuff like that before. So very insoluble. Why is there the difference here? What am I trying to communicate to you with this difference? Like this is a different functional group, right? So I have a bunch of functional groups on there. Is it going to help its solubility? No, no, because it's an insoluble functional group, right? It's not a polar functional group. Okay, so you need something that can make hydrogen bonds for the functional group for this to help. Okay. Okay, so let's rank the boiling points and melting points or solubilities of a set of compounds. How can you do this? Exactly. That's perfect. Yeah, you want to look at the size of the molecules. In this case, they're all very similar, but the molecular weights are going to help a little, right? The ones with more chlorines will be a little higher molecular weight, and so they're going to help that in terms of the melting and boiling points. They're not going to help in terms of solubility in water, right? Okay, so where do you start looking for solubilities? Yeah, you're going to want to look at the 3 to 1 and the hydrogen bonding. That's this one right here, right? Maximum solubility. You're going to want to look right here. We have a hydrogen bond again. That can do hydrogen bonding, right? But it's not the 3 to 1, is it? So that's fairly soluble, but not like compared to the rest of these is more soluble than those because we can do hydrogen bonding, right? And then we'd go down to dipole-dipole interactions, right? And so we'd start looking at the chlorines. So the first thing we want to look for is an overall dipole in the molecule, right? This one here has an overall dipole in the molecule. That one's not going to have an overall dipole, is it? Because they're straight across from each other, okay? There will be points where you're going to just get to the point where you can't really differentiate what is actually going to be better or worse. Like in terms of solubility, this, this one, this one are all pretty miserable. Okay. This is going to probably be pretty soluble, probably even miscible. This one is not considered usually soluble, but it'll be more soluble than the others. Okay. But like these are not going to be a huge amount of difference in solubility. they're really insoluble. We shouldn't expect much of, or if any, of that. Now, in terms of boiling points, which would you expect to have a higher boiling point? Yeah, the heavier one has the higher boiling point, right? That's the chlorine. Okay. The lighter one has a lower boiling point. Okay. And then you'd start looking for things like surface area versus branched. Okay. In this case, we don't have anything highly branched to cause interference for us. But yeah, this will be higher than this one. Yeah. I was just comparing two. Yeah. And so what you want to do is you want to get it down where you just systematically move each one. So for boiling point, you'll look at the hydrogen bonding, right? Most hydrogen bonding right there. And then you'd go, oh, that's another hydrogen bonding. The molecular weights are not hugely different, right? So that'll be the next one. And then you'd go down, oh, this one's a dipole. And so that's our next one, isn't it? Okay. Like the highest molecular weight and dipole as well. Okay. But that's not going to overwhelm a hydrogen bond. Okay. And then you go down here. Okay. So do we have any more dipoles? No, we're out of dipoles, aren't we? Okay. And so now we go to molecular weight. And then we just do it by molecular weight, don't we? Okay. And surface area if you have surface area differences. We don't have much of a surface area difference here. So. Anybody have any questions? This one's kind of interesting for surface area, by the way, because this 6-member ring is flat. So they're all going to go like this. Mm-hmm. So in terms of boiling point, you'd want to look at which one has an overall molecular dipole. Yeah, next to each other like 1/4. Because these will cancel each other out in terms of dipole. Okay. Very good. So let's talk about sort of an overview here. I'd already talked about this, but again, you want to go down in terms of what has the stronger intermolecular forces versus weaker ones, okay? Now, this can be a little bit complicated because the induced dipoles, when you have small molecules, they're going to be weak, okay? And so they'll always be the weakest, and you don't have to worry about much, right? If you start getting into like 20, 30 atoms, or God help you if you get thousands of atoms, these induced dipoles get big, okay? And that's why, for example, like in proteins, you can have nonpolar regions that literally squeeze water out, okay? And create like entire systems that are nonpolar hydrophobic, right? Like you have the dual layer cell membranes, right? So keep that in mind that in this class, induced dipole, they're always going to be weak. We're never going to be huge molecules. This is a huge effect. But once you start getting into like biochemistries and polymer chemistries and that sort of thing, they become massive. Okay. And it's like a million strings versus a rope, right? The strings are going to overlap. Okay. And this is that same order we had talked about in 4. It's just in terms of strength, right? This is going to have the higher boiling points. This is going to have the lower boiling points. Highest melting point, lowest melting point. Solubility, we're trying to match the strengths. Okay? So if soluble in water, we want to match hydrogen bonding, right? Okay. And so again, you'll want to assign that relative order. Notice I just was going through. I wasn't trying to reorder them in any way whatsoever. I just was going, this is going to be number 1, highest, next highest, and so on. I highly recommend you just sort of go, 1 is my highest, and then do 1, 2, 3, 4, and just go through those. Okay? It'll help you keep track of them if you have a lot. Now, the next thing you want to do is determine the most important intermolecular interaction between the molecules of each compound and arrange the molecules according to that intermolecular interaction. And so that's what we were doing before, where we did the hydrogen bondings, right? And then we discussed the dipole-dipole interactions. And then we discussed the, these are nonpolar, aren't they? Okay. All right. So once you do that, you can then start ordering them within the groups and lay them out. Okay. Now, right here, this is actually that order, and it has the boiling points next to them for reference. And notice there are actually huge differences up here, aren't they? Yeah. The differences fall off a bit here, but like they are significant. Yeah. There's enough molecular weight difference. You're going to see that difference. You could distill these from each other. Okay, so rank these compounds, A to E, the lowest solubility in hexane to the highest solubility in hexane. So we're doing it almost the exact reverse of what we do with water, right? We want solubility in hexane. Okay. What's hexane, by the way? Nonpolar. We want something that's going to do nice London dispersion forces, right? If it has stronger interactions, it's going to pull itself out. Okay. Do your best. Best you can. Okay, folks, I'm going to go ahead and go on since there's a lot of people that dropped the pen. All right. And so we look at these, and again, what are we looking for in terms of the most soluble? Lack of polar and dipole, right? We want something that's just going to have induced dipole, right? And so D, that's going to be on the top of our solubility. Okay. And then we start looking through here, and we have hydrogen bonding. This is going to be dipole, right? And so those are our groups then. Okay. And so there's our groups. We have D, and then we have AE, which are polar dipole-dipole interactions. And then we have BC, which would be hydrogen bond. So those will be the least soluble in hexane. Okay. We go ahead and start organizing those within those groups, and we lay them out. Okay. And so, for example, which one here is going to be more soluble in hexane? Be less hydrogen bonding, right? This one, too much hydrogen bonding, right? See? So there's a bit of a difference between polar and nonpolar versus hydrogen bonding. And the important difference here is that you have to remember that these OHs are like this. Okay? So when you're looking at those OHs, they don't actually have, they're not actually going to be like this. They're actually going to be like. And in the case of hydrogen bonding, because it's so localized with the hydrogen bond donor and acceptor, where they literally overlap these things. In fact, even that is not going to be a major deal. So in a hydrogen bond, you actually have your dipole contained within the hydrogen bond. Whereas in a dipole-dipole interaction, it's the whole molecule. Does that make sense? And so, having a bunch of hydrogen bonds that would cancel each other out for your total polarity for your molecule actually kind of doesn't matter. Because as long as they can do the overlaps, it just is never going to become an issue. And in fact, these things are so strong that let's say you did have that structure and it tried to overlap, and the only way it could overlap is like this, it'll actually move the bond. So it'll actually flip to a whole new structure in hydrogen bond. And it actually will not matter what the geometry is as much. Really strong dipole-dipole interactions can do the same thing, by the way. I had a molecule I was studying once that we were having trouble figuring out the geometry for it because of this. We actually had a bunch of fluorines around a group. So there's a fluorine and an oxygen on this carbon. And it was such a strong polar difference with that fluorine and oxygen taking electrons from the carbon that actually completely rearranged the molecule around. So it can do some pretty crazy stuff with enough, but I think I covered the issue, right? We'll stop going. All right. And so this right here is the order. So the hydrogen bonding is going to be the worst at going into hexane, right? And then the more hydrogen bonds, the worse it is. And then this one right here has the largest dipole. This one has the lower dipole. And then that one doesn't have a dipole. So it's just nonpolar. Okay, so let's talk about protic versus aprotic solvents. Now, you can be very polar. You can be extremely polar. And you can still be what's called aprotic, meaning it doesn't have a proton to focus that polarity on. Okay? Okay, so for example, here we see NaCl. It is highly soluble in water. Okay, everybody knows that one, right? Salt water. DMSO, on the other hand, that's the stuff in the patches, by the way. So it can dissolve through your skin, cross the blood-brain barrier. Everybody kind of knows what I'm talking about, right? Medication patches. That's DMSO. So it is a highly polar solvent. Okay, it has a huge dipole moment, 4 debye, versus H2O, which has a 1.9 debye. This actually goes into what we were talking about just now. Is that's a protic interaction right there, versus the aprotic, massive dipole here. Okay, huge dipole, right? Like 2 times. Okay. And so, yet it does not dissolve NaCl very well. It's actually quite poor at it. All right. And so what we're looking at here is that it's not just the magnitude of that dipole that plays these effects. Okay? It's how it actually can structure and overlap. Right? It's how close these polar charges are in that polar solvent and how they can actually get to the ions. Right? So let's look at this with a nice picture here. Okay, so if we did this with, here's our salt, table salt, NaCl, and it's being dissolved, solvated by water here, okay? And see how many can go around. Everybody see that okay? 6, right? And why is that? Well, it has very contained charge, right? So we can get really close together and packing around that very nicely. Now, here's DMSO here, okay? And you see that we can fit 2 less here, can't we? And so we can only fit 4 around here. And these partial negative charges are pretty accessible. But when we start looking at these partial positive charges, they're incredibly diffuse. And so we actually fit very little of the partial positive charges around those chlorines. Now, what that's going to mean is every time a chlorine gets near one of these sodiums, it's going to try to pull it out. And you're going to get that back as a salt. Okay? Uh-oh, we have a problem, don't we? All right. And so this is what's called, this is steric interference or steric hindrance. It's where the structure causes these things to interfere with their interactions. Okay? Or in this case, we have the bulkiness of these methyl groups here. And this is causing these to actually, because they're all the same charge, they're all positively charged, they're going to repel each other. And so you can't actually get them as close together as you would want. Okay. Okay. Anybody have any questions about that so far? Mm-hmm. Okay. All right. Now, the water, this is going to be a protic solvent, i.e. it has a proton and H donor. So it has an H bond donor. Okay. And that's what protic solvents are. They have H bond donors. Solvents that are like DMSO and do not possess H bond donors are called aprotic solvents. And so they can have like hydrogen bond acceptors. They could have extremely high dipoles, but they still don't have an H bond donor. Okay. And so they're aprotic. A meaning not protic. Okay. Protic solvents, on the other hand, could have a lower dipole. They could even, technically, they could have no H bond acceptor, but that's very, very unusual. So just know that that's pretty unusual. However, they have an H bond donor, and so that's a protic solvent. Okay, let's talk a little about lipids. You probably have all heard of lipids, I think. I don't know how much you've learned about lipids at this point in your careers. So there's going to be biomolecules. These are going to be relatively insoluble in water. That doesn't mean completely insoluble. Some lipids have some degree of solubility, but very, very little. Okay, typically considered insoluble. Most lipids are going to be nonpolar. They're going to be hydrophobic compounds, meaning not water soluble, right? And lipids are going to be divided into subclasses. It's going to be based on the structural features they have in common. We have the fats. Everybody knows fats. I have plenty. Thank you. We have the phospholipids. Does everybody know phospholipids? Yeah? Okay. Anybody not know phospholipids? Okay, they're typically what you find on your cell membranes. Okay. Steroids. Everybody's heard of steroids, right? Okay. The athlete abused steroids? Okay. Waxes. Does anybody know waxes? Can you find a wax currently? It's true. Yeah, you got me. This is also a wax right here. The bee honeycomb. Okay. So fats, oils, and fatty acids. Fats can be of animal or plant origin. Animal fats, such as lard, are usually solids at room temperature. Fats from plants typically are liquids at room temperature. These are usually called oils, and that's where you get most oils. However, we as animals do also have oils. It's your skin oils, which are liquid at room temperature. That division is a little, you can argue. The most common biological functions of fats and oils is actually to store energy. That tends to be the most common. However, you can have other purposes. Our oils on our skin actually have a number of different purposes. They actually feed the microorganisms we need on our skin. So technically energy there. But they also help protect our skin from various different things, right? And so, yeah, multi-purpose. Doesn't always just have to have one purpose. These fatty acids right here. These are going to be fats. They contain fatty acids. They help regulate blood pressure, blood lipid levels. They play major roles in the inflammatory response to injury. This is actually a relatively new field that's being highly studied. Is the role of fats in the inflammatory response and thus the stress response of the body that can then cause difficulties in healing and immunoresponses and all sorts of other stuff. Okay. This is where all that seed oil stuff started coming in. By the way, did anybody know what the most common fat used in the 1950s used to be? Huh? It was actually lard. Yeah. Mostly from cattle, but whatever animal. It was actually in the 1970s and 80s, the current health consciousness of the time dictated animal fats were bad for you. And so the reason all the restaurants in the United States use seed oils is actually seed oils were not the original fat they transferred to. They transferred to peanut oils first. And then the health advocates at the time said that was bad, transferred to seed oils. And seed oils have now been found to be worse than both of those. And actually, lard was better. So, um, yeah. Anyways, is not exactly a very well researched science. Still isn't, but it's better. We're getting better, slowly but surely. Thank goodness. Anyways, this right here is like coconut oil, palm kernel oil right there, and you can see these are various different oils. As we get longer here, these are going to get to the fats that are going to be solid at room temperature, right? Because we're going to increase the number of induced dipole interactions. Okay. Anybody have any questions about that so far? Okay. Anybody know what that is right there? Double bond? Double bonds, right? So if you look at this chain right here, you could say maybe it's like it's saturated with hydrogens, right? And if you look at that, it has a place where it's no longer saturated with hydrogens. What do you think that's called? Unsaturated fats. Yeah. And so that's saturated fats right here, unsaturated right here. Okay. Triglycerides. So fats or oils contain three adjacent ester groups, each of which can be produced from a fatty acid and an alcohol group from glycerol. When it's all together, this can be called triacylglycerols or triglycerides. Okay. And that literally comes from this ester group right here. So again, this is glycerol. These are the fatty acids right here. They can be various different ones or the same one. Doesn't really matter. Well, it matters a lot for you, but in the general scheme of things, it doesn't matter. This right here is then the fat or oil that you typically would get from an animal, plant, or whatever. And this right here is the triacylglycerol. Okay. This right here is going to be phospholipids. You'll notice it looks very, very similar, right? Can everybody see that part? It's the exact same, isn't it? Okay. And the difference being it has a phosphate. Yeah. So a phosphate is bonded to that last OH of the glycerol. And so that's the phospholipid is going to consist, again, of the glycerol backbone, two fatty acids, and an ester linkage. Notice it has two tails. Those two tails are actually why they're used when you make cell membranes. Okay. Everybody have that structure okay? Right. This part is going to be this ionic head right here. Oftentimes, this phosphate is going to have something attached to it. In this case right here, we have a choline fragment. Okay. And it'll make it more polar. Or another way of saying that's ionic, so it's even more separated from being able to dissolve in, fatty acid tails, right? The nonpolar tails. Okay, so hydrophobic tails, hydrophilic head, right? When you put these in water, what do you think happens? Well, what's going to happen is they're going to arrange in such a way that the polar heads will point out towards water and bond to the water with hydrogen bonds. The nonpolar tails, on the other hand, are all going to orient towards each other, and they'll dissolve each other, okay? And because you have two tails, they can't make a really tight turn, okay? If you had one tail, they can make a very tight turn, and that would form what's known as a mycel. And it's a one-leg, okay? That's how, like, soap works, but that's also how you extrude stuff into your blood, like stores of fats and things when you're trying to transport them, okay? Okay, so this right here is your cell membranes. Again, it's going to be phospholipid layer. We have the aqueous environments on both sides. And it's going to be formed with the tails going all the way around like so. And the polar heads facing outwards, right? Everybody okay with that so far? Okay, fantastic. Note that like non-polar things like cholesterol can be directly embedded with these tails. And those are actually used to change how mobile this is. Keep in mind that these things are usually liquids at room temperature, right? So this is actually more like a liquid than a solid, okay? So we're actually more like bags of liquids surrounded by other liquids that are kind of like just on the verge of popping all the time. We're kind of precarious. That's why any time somebody like pricks us too hard, we pop. Okay. I know it's unpleasant, but it is a thing. Okay. Now, this again, cholesterol, this would be like an integral protein. What that has is a non-polar sides that can run through the membrane, and then usually polar heads to keep them anchored at the two slots. Transmembrane protein, cytoplasm is right here. That's the inside cell. This would be outside. Okay. Anyways, I'm just going to cover it to that level because not biochemistry. All right, now steroids. These have a wide variety of biological functions, but a very unified structure, actually. Okay, very, very unified. So they're going to help maintain the cell membrane. That's actually cholesterol. They're going to serve as sex hormones. That's testosterone and estrone. They're going to regulate blood pressure, aldosterone, and treat inflammatory conditions, cortisone. They have a huge variety of purposes. Biochemistry will be an interesting class if you're interested. Okay. Now, all the steroids all have the same basic structure, which is this ring structure right here. Okay. And notice it's 1, 2, 3, 6 member rings, and a fifth 5 member ring. Okay, a fourth 5 member ring. All right. So this is A, B, C, D. They are always numbered the same way so that you have a consistent structure to work off whenever you're trying to describe them. And this is the different steroids that we had discussed just now. So this one's cholesterol. It's considered like the base steroid. Does anybody know if you need cholesterol? You most definitely do. In fact, increasing cholesterol in your veins due to heart disease is not the cause. The cause is you have damage to your veins, and your body needs cholesterol to repair them. Okay? Now that repair goes awry, and you start clogging your veins with cholesterol. But you need to treat the base root if you're ever going to treat that. Okay? Which is you're damaging your veins all the time, usually because of high blood pressure. Okay? Just removing the cholesterol is not going to treat it. Now, this right here is a wax. It's the principal component of beeswax, actually. And we actually see here a bunch of different waxes, obviously that being earwax for humans. But have you ever looked at an apple and it's all shiny looking? Okay, fruits, they're shiny looking. Why are they shiny? They coat it with wax, right? Plants are shiny looking because they coat the tops with wax. And it keeps the water from absorbing in, right? Because wax is nonpolar. Okay. And so that's what you're seeing there. Fantastic. Excellent. Okay, I'm gonna